My name is Lucas Amorim, and I'm an AppSec engineer, and I do some security researching and exploit development. Today, I'm going to be talking about the current state of exploit mitigations in the Linux kernel. So the whole idea of this talk is to give overall overview of mitigations in the kernel and how they can be bypassed. So we're going to be, as an introduction, we're going to be talking about a few concepts in the Linux kernel that's going to be necessary to understand the mitigations. So the first one is the kernel memory space. So the Linux kernel and most of the modern operation systems kernels, they separate the address space in two categories. One is the kernel land, the kernel address space, the other one's user lands. So in this slide, we can see that we have some space allocated to the kernel in the higher addresses. And we also have the user space applications running in user land in the lower addresses, right? And the whole idea is the kernel should never directly access user space, and user space should never access kernel space unless it's using a system call, right? For example, when the kernel wants to access some data from user space, it has to copy that data into kernel land and do whatever it has to do with that data. And then when it wants to send some data to the application, it has to copy that data to the user land memory address, right? So if you take a look in the Linux kernel, there is a couple functions. It's copy from user space and copy to user space. So those are the ways you manipulate memory between the kernel land and the user land. And then we're gonna see later why we need that. So first thing, the way the kernel allocates memory in the heap is using the function called Kmalloc, which is similar to malloc in the glibc, which allocates a chunk of memory in the kernel address space, right? You can specify how much space you want, and the kernel will find one on a kernel cache that can fit the amount of memory you are requesting. So sometimes you might request I don't know, 32K of memory, and you get more than that because the kernel cache used to allocate the data you requested was bigger than that, because the one before that one couldn't allocate 32 kilobytes of memory, right? And same has free in glibc. We have kfree that releases memory that was previously allocated in user land. In kernel land. Right. So one thing is really interesting about the kernel, and I thought it was a good idea to bring that up, is the ref counters. So the reference counters in the kernel. The reason why I'm bringing that up is because there's a lot of vulnerabilities related to reference counters, and then we're going to be looking at one in this talk. But what it basically does is it's an integer that can only be modified by atomic updates. What does that mean is only one kernel thread can increase or decrease that counter at a time, right? So it has a lock around it. There is a function called atomic underscore increase ICR and atomic underscore DCR, if I'm not mistaken. So those two functions are used to increase and decrease the reference counter. And the reference counter mostly used to when you have a piece of memory that was allocated in the kernel, and then you have different subsystems or different areas of the kernel using that. So we got to keep a reference, so we make sure that we don't clean that memory up before all the other while we still have other areas in the kernel, other subsystems or functions or whatever using that, right? It is a way of avoiding things like double free or use after free. But it can also be a problem because sometimes it can get out of sync and it can be released while still there is other areas of the kernel using it, and we're going to see that later in this talk, right? So the way that the kernel memory management works is the most used is lab. Lab is the memory management, and is also the chunk of memory that it is allocated to you. So both things, the way that is allocated, the code, it's called slab, and also the chunks of memory is also called slabs, right? And there are other two different ways of allocating memory. It depends how your kernel is being compiled, but the default it's slabs. So here we have an example. So basically what a slab is, it's a linked list of chunks of memory. So in the memory, in the kernel memory cache, we'll have the size of those slabs. Let's say we have a slab that is 32K. They all gonna be in the same linked list, one point to another, and they're going to be linked to some sort of free list. And then once they get allocated, it is removed from that linked list and is placed in the in-use list. And once it gets released, it goes to the front of the list. So let's say if a chunk of memory was allocated and then released, it goes right to the front. And if it gets allocated, another request to allocate the same amount of memory is received, most likely we reuse the one that was previously freed. Right, so here we have a better understanding. So we have the full. So the full list means it's a linked list with all the slabs used. So they all have been allocated, and the partial has slabs that are used and the ones that are free. In a free list, all the slabs that list, they are all free, right? Let's move forward. All right, so today to explain how memory corruption in the Linux kernel works, we're going to be looking at this is old vulnerability, but it was fixed in kernel mainstream, the main line of the kernel, but a lot of the distributions used older version, and they did not backport that fix back to their kernels. So there were a lot of systems vulnerable up until like 2 years ago, 3 years ago. Right. So what happened that vulnerability is in the keyring subsystem. So the keyring is used to store credentials in the kernel. Let's say you have an application and you need to store some credentials, and you want to make sure that other applications in user land cannot access that credentials in memory. Because it's going to be stored in your memory. So what you do is you do a system call and you ask the kernel, say, hey, can you store these in kernel space and only let my process, myself, to access? And then you can also do other system calls, and you can say, okay, all the child processes can also access this secret. So, and that's where the problem begins, because every time you have, let's say, the process is forked, and you have another process trying to join that keyring. So the usage field, which is a reference counter, was increased, but then the bug happened when you are already you already have access to that keyring, to that secret, and you keep requesting access to it, right? So what happened is every time you request access, the reference counter was increased, and then it would fail because you already have permission to that secret, but it wasn't getting decreased, right? It was being incremented, and it became an integer overflow. So you wrap around to negative numbers and until it got to 0. So if you keep requesting over and over again, it would keep increasing until you have an integer overflow, and then you ended up with the usage 0. And at that point, the kernel garbage collect will just clean that up with basically key-free that chunk of memory that you had, but you still have a process running pointing to that specific slab. So that key ring was stored, was allocated in one of the slabs in the kernel, and then after the integer overflow, it was removed, but you still had a user space process, and therefore also like a kernel keyring process thinking, assuming that the data is still there, is still valid, right? So if you can make the kernel allocate something else on top of that, in that same slab, you might be able to get the kernel to execute a function that is controlled by you. I hope that makes sense. So the whole goal, the exploitation goal to privilege escalation is to get to this. It's called prepare kernel cred and commit creds with 0. That would make the current context being invoked to become a root, to become administration in the system, right? So in every single local kernel exploitation, local kernel exploit, not every single, most of them, the goal is to call those two functions with the kernel. And those functions are not, you cannot call that from user space. You need to find a way within the kernel to get that executed, right? And so one way you could do this is basically, let's say you have your key ring being allocated in the kernel space, and then it gets, there is an integer overflow, and then it's freed, and then you are able to actually allocate some memory in its place. You can use something like send message to the kernel that would try and send messages, and then you can put your payload there. And in the key ring, for example, it has function pointers, which means it's a field, is a pointer to a function in memory. So you could call system send message, sending that payload with a function pointer, point to a function that you wrote in user space, and that function would try and access commit kernel creds and prepare kernel creds, right? Because it's still in the kernel context. So that's what they call the read to user. So basically returning to user space. That was a way that exploit developers used to write kernel exploits back in the day. But then there was a mitigation for that, which is map. So is map does not allow the kernel to call functions in user space. And same way, there is a variation of map called map that with an A that doesn't allow you to access memory in user space. But the important one right now is map with an E, where basically if the kernel tries to call a function in user space, it would fail. Its map will prevent that. And the way it does this is by checking the CR4 register. So it checks if the one of the bits, this mat bit in the training position, it's set. If it is set, it means that's running in kernel space. That way, its map is enabled, and then you cannot invoke a function in user space. You could try and find a gadget that will change the value in that bit, so the kernel would think that you are in user space, but that can't mess up the whole system, make the whole system unstable, and then you might have your kernel crashing. So it's not really at least as far as I know, as far as my experience goes, it's not really a stable way of writing a kernel exploit, right? And now, of course, you can check whether SMAP is enabled in your system. If you're running a modern kernel, for sure it is enabled. So you can check in /proc/CPU info. Or if you have a kernel dump for a crash, you can analyze that. You can connect that with GDB, and you can check the value of the CR4. All right. So the kernel page table isolation, it's somehow new. It was came out of I would say about 2 to 3 years ago. It was a mitigation to meltdown, and it turns out that it does something really similar to SMAP. It prevents you from reading or user space mapped and basically making all the user space memory not executable. This way you wouldn't be able to execute a user space function. It's not that it's preventing you to execute. It's not like SMAP, like blocking you from executing. It's more like making now the user space page, memory page, not executable. So this way you cannot execute any function. Therefore, you cannot become root. So it's similar to SMAP, but it was more. It was built for has a mitigation to meltdown about 2 years ago. But it turns out that is also protecting. It does something similar to SMAP and also protecting against some of the kernel exploitation techniques. Okay. So, all right. Now let's work with the bypasses, right? So the way we can bypass SMAP and kernel page table isolation, it's by basically building a gadget. Okay, so similar what we do with the user space gadgets, we can go and we can find the small the assembly instructions within the kernel, and then we can build it up, the whole execution, the whole flow of execution using assembly, only using kernel space address. So if you look at this example, they are all high addresses, which means there are instructions stored within the kernel user lanes. So you can go and you can build your whole execution gadgets, and you can get your commit credits per kernel credits by just using the gadget. So that's a bypass in Office Map and case kernel page table isolation. It works really well. You can definitely bypass, but on top of that mitigation, there are more other mitigations, so they all add up and trying to build a secure, a stable exploit mitigation chain. All right. Okay. So again, here we have an example. So in the previous example, we had all the addresses here that I'm building the gadget, and then I'm just building my payload, and I can put that, let's say, in my the data I'm gonna send to the kernel use send message, and that's gonna get allocated. And then I just want to make sure that my gadget starts in the same offset has the function pointer I'm gonna be the kernel thinks is calling, right? So let's say, for example, the key ring, it has a function pointer to a function called revoke, which basically revokes the key ring. So I need to make sure that when I send my payload, it's well aligned that my gadget starts right at the offset of that function. So when the kernel calls that function, it actually goes to my payload and start executing my payload, right? All right, so how can we prevent that? How can we prevent, ROP, return-oriented programming in kernel exploits, right? So the way we do this, it's a similar way we do that in the user space is by basically using an address space layout randomization. So KSLR, so it's KSLR is equivalent to ASLR in user space. So what it basically does is, well, every time you boot up your kernel, it's gonna create a number, and you're gonna use that number to randomize your address. Let's say, just as an example, if your number is 2, and then you have a function at position, I don't know, position 10, right? When the kernel, when KSLR is disabled, if that function is, let's say, stored at position 10, and then you enable KSLR, and then KSLR generates a number during boot time and adds that. So that function now is no longer at position 10 in memory, it's going to be in position 12, right? That's a really simple example. So what KSLR basically does is that, like, it's basically randomize your kernel address space to prevent vulnerabilities to be exploited, prevent ROP payloads to be exploited, right? And that in my experience, it's been the most annoying part of writing kernel exploits, because now you no longer, one vulnerability in the kernel is probably no longer enough. You're gonna have to chain a couple of vulnerabilities together, because what we need now to bypass KSLR is to find an information leak. So we're gonna find a leak in the kernel, a function that an error in the kernel that's leaking a function address, right? So once we have that leaked, we know in which position that function is being stored. And then as we disable KSLR, when you're writing the exploit, you disable KSLR, and then you see in which position that function is being called. We store that position, and then during the exploitation time, your exploit is gonna do you're gonna exploit the information leaks out that function address, compare that to the one, the static that is when KSLR is disabled. And then you will define the offset, and then it's going to kind of move all your ROP gadgets, use that offset to put your ROP gadget in the right position. So it is important that when you are writing an exploit, you need to disable KSLR to find the real function address, and then you enable it, and then you see to which one it's going to go to. And of course, every kernel, it's different. Every machine is going to be different. Every time you reboot your system, is going to be the addresses will change, and that will make the exploitation much, much, much harder for you, right? Yeah. So as I mentioned, like, you gotta find an information leak that leaks the address of a kernel function, and then you're gonna use that as your offset to calculate your offset to find the other function's address. And if you want to disable KSLR, you just need to pass no KSLR flag during boot, and then find the address for the previous functions, right? So the way I try to, when I have a vulnerability in the kernel and I'm trying to write an exploit, I disable all the mitigations, and I write the exploit, get it to work, and then one by one I start adding the mitigation, try to bypass. So usually I add the SMAP and kernel page table isolation. I added those two, and I try to build my ROP gadgets. And once I have that, then I need to bypass KSLR. This is a really simple example right here. So if you see up top, it's a Python script that has address, which is, as you can see, is in the higher address, so it's in the kernel land, right? That's the address when KSLR is disabled. So what it does is try to leak that address. It's trying to leak. It enables KSLR, leaks that address, and then subtract that the leaked address with the static one, and then we know the offset. So we know the KSLR is light. So by how many bytes we have to slide our ROP gadgets addresses. So that's it. I hope you all enjoyed my talk. Thank you very much. And if you have any questions, feel free to reach out anytime by reach out on email or Discord, or just feel free. Thank you.